Joey, can quantum mechanics actually break time? We think of time as a simple straight line, a fundamental rule of the universe that flows in one direction, from past to future. An egg shatters, it never unshatters. We have memories of yesterday, but not of tomorrow. But what if that's not the full story? What if, at the deepest level of reality, time isn't a one-way street? What if it can be bent, twisted, and maybe, just maybe, reversed? And no, this isn't science fiction. This is the strange reality of our most successful theory of the universe, quantum mechanics. The quantum world is bizarre. It's a place where particles can be in many places at once, where simply looking at something can change it, and where two particles can be mysteriously linked across the entire cosmos. It's a place that seems to delight in breaking our common sense. So, what happens when this weird, microscopic world crashes into our basic idea of time? The results challenge everything we think we know. They hint that time travel might not be so impossible after all, but in a way you'd never expect. And it forces us to ask an even bigger question: is time even real? Section 1. The Arrow of Time. Before we get into the quantum weirdness, let's start with something we all experience: the arrow of time. You spill your coffee and it makes a mess. You see a building fall, but you'll never see a pile of rubble spontaneously become a skyscraper. Physicists explain this one-way street using a crucial law of nature, the second law of thermodynamics. It basically says that in any closed-off system, things always get more disordered. This measure of disorder is called entropy. A perfect sandcastle is eventually worn down into a messy pile of sand. The universe itself is moving from a state of low entropy to high entropy, and this relentless march towards disorder is what gives time its forward direction. It's why the past and future are different. For more than a century, this was the story of time, simple and irreversible. But this neat picture unravels when you look really, really closely. The fundamental laws of physics that control individual particles are mostly time-symmetric. They work perfectly forwards or backwards. A video of two billiard balls hitting each other looks normal, whether you play it forwards or in reverse. So if the tiny fundamental laws don't care about which way time flows, where does our arrow of time come from? That's one of the biggest mysteries in physics, and the answer might be hiding in the quantum world.